a good time, and today it's an important continuation of very important tutorial by Michael Cuturi, so please.
Thank you very much. So good morning everyone. I hope you had a good night of rest. So today we will continue this and finish this tutorial on optimal transport. I just wanted to say a reminder that the slides are on this link if you follow them, bit.ly/MLSS19OT. And so please feel free to download them and maybe look at them if later in the MLSS if you're interested. So what I will just go back to today is, so yesterday we had the tutorial, so you had a bit of a feel of what it means to solve optimal transport using a standard solver, and then what it feels like doing it with the Sinkhorn algorithm, which you can implement in a few lines. So I would just like to start the tutorial this morning, the course this morning with just a little reminder of what you did yesterday, and then show you that there are a few things you can do beyond computing the distance or using this approximation of optimal transport to do this interpolation between points, color transfer. And the main subject of this morning will be how to backpropagate or differentiate this Wasserstein distance. So yesterday you computed this distance to, for instance, compare documents or interpolate between two color palettes. Today we are going to use the Wasserstein distance as a loss function, just as if we were, for instance, using a loss function between vectors, except that this time we will use it between probability distributions. And we will see what you can do with such a loss that you can actually differentiate. So remember the main motivation for this Sinkhorn algorithm was to provide a simpler, faster way to approximate optimal transport. Not go the linear programming route, but simply find some alternative. And I told you that one very natural alternative was to regularize. So this is a topic that I think you will see is a fundamental topic in machine learning and more generally in statistics. We usually define an optimization problem that plays with data, confronts data with some model, and in the simplest of cases that is enough, but in most cases you need to add some regularity prior. And so you see it, for instance, when you do regression, linear regression. If you do linear regression in high dimensions, you need to add some regularity to your coefficients. And this is typically done by doing the lasso or rich regression, or there are so many variants of penalized regression. So here it's the same philosophy that's playing. We have a problem which is this optimal transport problem. It is well defined in terms of an LP, but usually we see that we might be overfitting. The transport that we get is sticking too close, is really working too hard. And so in machine learning, we're not optimization people. We don't care so much about getting to a highly precise solution. We are happier, not only for computational purposes, but also for statistical purposes, to stop earlier, to do something that's cheaper. And so the way this is phrased here is by adding this regularity, this entropy. And so at least on paper it makes sense. What it looks is for a transport matrix that is more diffuse. And what it makes the most sense for, I guess, also is computationally. Because as you saw yesterday, what this boils down to is just simply two very simple updates that can be computed using a matrix vector product. So this was what I walked you through yesterday, and that you actually implemented. I think you will recognize in line 1 and line 2 those two instructions that are central to the Sinkhorn algorithm. So what I wanted to insist is one of the reasons the Sinkhorn algorithm is popular in applications is that it's very easy to implement. You've experienced it yourself. So the way the Sinkhorn algorithm works is it takes two probability distributions, one called weighted with weights A and weights B and then locations x and locations y. What it only needs is the vector of weights A and B and then the kernel matrix that stores all of the pairwise information between the points in the first measure and the second measure. And then it just loops through some very simple sequence of operations. You divide the vector of weights A by the matrix K times some initialization, you get something. Then you multiply that by K transpose and divide B by that and you get something, etc. And so you can look at this like this alternate projection, alternate optimization scheme. So the question is, how many of those iterations do you need to do in practice? And the question is directly linked to epsilon, actually, to the strength of the regularization. So in some way, there's no free lunch. Here, I'm trying to solve a problem that will look like optimal transport as gamma goes to 0. And that will be trivial to solve as gamma goes to infinity. As gamma, remember, when gamma goes to infinity, we recover the story about the general sending soldiers just proportionally. They just don't care. They don't really coordinate. They just send everything proportionally. And as gamma goes to 0, we really go to the real solution of the optimal transport. So what I wanted to say is that when gamma goes to 0, this Sinkhorn algorithm is maybe not the most efficient way to solve the true original optimal transport problem. What we will be seeking and looking for is rather to be in a regime where we're happy with some regularization. Okay? And in this case, in this area, for instance, this will be infinitely cheaper to obtain than this thing. I mean, not infinitely, but several orders of magnitude cheaper to obtain. So, the other part of the story that I wanted to tell you is that once you do those Sinkhorn iterations, and this is what you saw yesterday, you can very easily recover an optimal transport plan, an optimal regularized transport plan, okay? The optimal plan for the regularized problem. And this is diagonal matrix times this K times diagonal matrix. And it's also very simple to recover something that looks like the optimal transport cost. What is that? Well, you remember the transport cost is just simply the dot product of the transport plan and the cost matrix. And so in this case, we can get something that's actually very cheap to evaluate. And the dot circle here in the middle is just the element-wise product of matrices. So if you want to evaluate the cost of this entropic regularized transport, you just do a vector matrix, a vector product, and then you get it. Okay? And this will play a role later, because in a few slides, what I will show you is that because of the very trivial nature of this algorithm, we have done very, very simple things with this algorithm. We've just done matrix vectors and inversions. We can very easily differentiate the output of this algorithm. It's just an algorithm that does a bunch of matrix vector products, a few element-wise divisions. So as long as the entries are not 0, it's very easy to differentiate all of that recursively. And it's easy to use PyTorch, TensorFlow, Chainer, I mean all of those frameworks to get the derivative of this cost with respect to any input of your problem. But I will get back to this. Another nice feature of the Sinkhorn algorithm is that when you compare several histograms that all have the same support, so let's say that all of the measures A and B respectively share the same support, then they share the same kernel matrix. Okay? And then all of a sudden, this Sinkhorn algorithm can be trivially parallelized, in the sense that instead of doing a vector fixed point iteration, so remember earlier I was starting with one vector v0 that would compute the distance between two measures, and I would be updating this vector v and the vector u. Here you can just stack all of those vectors together, and instead of doing multiple times matrix vector products, you just do matrix products, and we know this is faster. And numerically, we have better routines to do matrix products because we can more simply map them onto memory and parallelize more easily, and this is what GPUs are good for. So one of the benefits of this approach is that you can very easily parallelize a computation of several distances when the kernel is the same. And so I'm doing this animation again just to illustrate my point, but I think you have understood it. Whenever you can vectorize things, whenever you can do matrix products instead of a big loop of matrix vector products, you should take the opportunity and take the opportunity to have significant speed up, notably, especially if you can have access to GPUs. So this is what we showed, and if you do this way, then basically you will recover that this Sinkhorn algorithm is orders of magnitude faster than the network flow simplex. So this slide is from 6 years ago, so it was in the first, my first work in this field. And at that time, for me, this was the main reason this Sinkhorn algorithm was interesting. It's essentially a huge speed up. So whenever you're fine using slightly blurred optimal transport plans and not the original transport plans, then you can get a speed up of, let's say, 1 million. Let me say that, to be honest, this is a bit an apple and orange comparison, of course, because it's not really fair to compare an algorithm that solves the solution to an unregularized problem to an algorithm that is solving something that's regularized. Okay? It's as if I was comparing regression and rich regression, or lasso and regression and lasso. I mean, it's a bit apple and oranges, right? However, what I wanted to say there is that from a practical perspective, if you're not really that interested in getting the right solution, this alternative is really, really much faster. So here I have a small animation that tries to give you an impression, an understanding of what's going on with the Sinkhorn algorithm, and notably what could go wrong. I would like to also insist that when you try to use this algorithm for the first time, you can make a few mistakes that make it go, off the rails. So it's a relatively dangerous algorithm to play with because of the exponentials, and numerically things can go wrong. So let me try to explain a bit. So here I have an example. Here I have an example where I'm going to do the following. I have two images, two squares, and a few of the pixels are lit up and a few of the pixels are dark, or basically yellow and blue. So blue means that there is zero mass at that location, and yellow means that there is a high mass at that location. Okay, so those are two MNIST digits, and I see them as probability distributions on the square. Okay, what I will do is try to compute the optimal transport between them, optimal transport distance between them. So you can imagine that you have a mass sand which is distributed along this line in the bottom and then distributed along the 7 above. And then I will try to use a Sinkhorn algorithm to do that. So let me just get a few things straight. What is the dimension that we're playing with? So here I think it's 28 times 28, so 740 something, 700, I mean about a few hundreds, okay, because I have a few hundred pixel locations, okay. All of those pixels have 700 choices to follow. So my kernel and the cost matrix will be 700 times 700. So although there are faster ways to implement the Sinkhorn algorithm there, and this is one of the papers that we wrote with Justin, I will here just simply do the naive thing, which is I will store the distance between every pair of pixels in this 700 times 700 matrix and use it as a cost matrix. So what does the Sinkhorn do? Sinkhorn starts with a vector, you remember, which is of the same size as your data. The vectors V's and U's have the same size as your histograms B's and A's here. So everybody here has the same size, so it's simple. This vector has the same size as an image, so I will just picture it as an image. So if you think about it, applying this kernel matrix to V is, you have this big 700 times 700 matrix, you apply it to this vector of times 700, and if you look a bit carefully, this application of a kernel is actually doing a Gaussian blur. And so this is why you can do it faster than actually multiplying the matrix times the vector. We have faster algorithms to do Gaussian blur than quadratic in number of pixels. So here you apply the kernel, and you remember the Sinkhorn algorithm, the next step is A divided by K times this matrix vector of weights, V. And so you would take just simply what's on the top left divided by what's on the bottom right. Of course, what is on the top left is essentially made of zeros and a few values that are positive where you can see the ink of the number. So what you get is this thing. It's something that is positive where there is some ink and zero elsewhere, right? And so you start seeing some values that pop up, you know, there is some slightly higher values at some pixels, but that's just still just the beginning. Because next, what you do, remember, is you have to blur the vector of weights above U, and you take B on the lower hand, lower left, divided by that thing. So here, this is where Sinkhorn starts being a bit tricky to play with. Because what I'm doing is I will be dividing the values on the bottom left, element-wise, all of the intensities in the bottom left, element-wise, by what's on the top right. And so you can see that there's a lot of almost zero values on the top right in the KU1, and I'm going to divide B by that. So what you can immediately see is that this starts a bit blowing up. I mean, it seems that this is not very numerically stable, because if I do bottom left divided by top right, I get values that are roughly equal to 10 power 8 for some of those pixels. So when I displayed this, basically the information somewhat collapses if I look at it and there are lots of values that are negligible if I compare it to the highest values of this thing. But that's fine. This is the idea of the Sinkhorn algorithm. I'm just going to do a blur again of what's in the bottom, and then I'm going to divide, etc. So as this Sinkhorn algorithm progresses, you feel that something's wrong. It's not working properly. Actually it is, but if you look just like on the top, maybe it's a bit hard to see on the screen, but the highest value is 10 to the power 36. And in the bottom, the highest value is 10 to the power 10. So you would think that maybe something is wrong. But actually, that's the way the algorithm works. And so if you keep on doing those iterations, you keep on having, you know, those values that seem to diverge a bit. And so what I propose is that we actually plot the logarithms of those vectors u's and v's. And what this is what the logarithm of those vectors u's and v's look like. And so immediately this seems to make a lot more sense, right? It's easier to visualize now that we've removed this exponential factor. So if you look at the logarithm of those vectors, basically what they are doing is keeping track of something you can interpret as being the dual variables. Remember that I told you about the dual Kantorovich problem? Well, this is what's going on in the dual variables. And here is something that I would like to give you, to share an intuition before we look at the math. Think about transporting the top left image to the bottom left image. So the 7 to the 1. If we were to actually take a shovel and move things around, what areas of the 7 do you think would be the most costly, the most bothersome, the most annoying to get back this 1? Well, if I look at the two images, intuitively it seems to me that areas where they more or less overlap might be easy to deal with, but that the areas where they seem to be far apart and the support don't overlap at all, don't share, and even so, if they are far away, are the most annoying. And if you look at the 7, well, it's pretty clear that the top of, you know, the left hook on the top is pretty far from anything that the 1 has to offer, right? And so that's probably going to be the problem. And then maybe the bottom or the rightmost part of the 7 are a bit annoying. And inversely, if I were to do the work from 1 to 7, I can imagine that the tips of the wand would be the most problematic. And actually, this is what is revealed in this picture. You can actually interpret those logarithms of u's and v's as if they were dual variables that actually quantify what are the areas that are the most painful, you know, to transport things. Even if you do your best and find the optimal transport, this is still very expensive. And this could start giving an insight on, imagine you were able to change a bit the 7 or the 1. What would you do to make them be closer in Wasserstein distance? Well, what I would do is look at the picture on the right, you know, the dual variables, and erase a little bit of this top left thing, and move it maybe closer to the center. And same for the 1, for the digit of 1s. I would maybe try to make it a bit shorter, and then gradually you see how you can actually improve the Wasserstein distance between these two things. And this is the insight we will be using next to optimize things with the Wasserstein distance. You will want to compute a gradient of the Wasserstein distance, and typically this will be given by values that look like this right-hand side of the Sinkhorn algorithm. So anyway, so just two things that I would like to highlight. When you run the Sinkhorn algorithm, very often you will get values that numerically seem to blow up a bit. That's normal, and it's probably because your epsilon regularization strength is too small. And the second thing is, there is a very natural interpretation to what you're doing, actually. And that interpretation is that, let me just finish this, maybe too many iterations, is that what you can reinterpret this regularized optimal transport problem in the primal as trying to solve a dual problem, which is the dual of this optimization problem on the top. So let me just, for those of you who are fond of optimization, let me just tell you that there is a very natural way to interpret the Sinkhorn algorithm as something called a block coordinate ascent in the dual. So you remember this, the primal was just minimization of the cost of the coupling. The dual of the transport problem was maximization of the expectation of some potentials under some constraints. When you regularize in the primal by this entropy, what you get in the dual is a regularization for those weights as well. So let me just a bit gloss over this because this is a technical point, but if you like optimization, it's a nice one. So now you remember that I told you a few things about transport and the original formulation of transport and why there were problems. One of them was computationally it's expensive. So now I have proposed a scheme that is arguably faster. It doesn't do the same thing, it changes the rules of the game, but it is much faster. Then there was a question about the statistical complexity. The other problem of optimal transport is that even if you solve this linear program and you get it right, it might be actually a waste of time because you're actually you're working too hard for something that's not stable enough. And so one of the alternatives was, is there another formulation of transport that is more stable? And so what you can see is that there are basically a few choices you can make with this regularization. So I'm taking again this cartoon of looking at where the solutions are in optimal transport. When you solve the optimal transport with high precision, with linear programming, you're reaching a vertex of this feasible set of transportation matrices. What I told you is that when you regularize, you are somewhere inside this polytope. And when you regularize maximally, when you put an infinite regularization, what you recover is just the product of the marginals. This is like this max entropy coupling that you can get. And interestingly, it turns out that the value of the transport at that product of marginals, the maximally entropic transport plan, is exactly what people call the energy distance or the maximum mean discrepancy that Arthur Gretton will be presenting in a couple of days, or maybe tomorrow, I think. Yeah. So let me again try to use my analogy with you remember the soldiers. So the generals have to send the mass to the front line. They do it optimally. This is like Wasserstein. This is optimal transport. They do it lazily without thinking about, the topology or how costly it is to send troops. They just split things proportionally, send everyone, and then look at how much energy they had to spend. And this is the coupling that is the product of the marginals. And once you normalize this cost of sending troops that way, you recover something that's called the MMD, maximum mean discrepancy. And now what I argue is that there is a third solution which is intermediate. It's a bit between. You want to hedge your bets. On the one hand, you don't want to completely optimize, but on the other hand, you don't want to be completely blind to the data. You want to take into account the fact that you can do a bit better, by adjusting your movements. So you're not going to a full linear programming and full optimized, and neither are you going to do something completely lazy. And so in each of those three situations, you can define a notion of distance between probability distributions by taking the right normalizations. So in the first case, in the optimal transport case, it's very easy. You can define a distance directly through the transport cost. In the MMD case, or energy distance case, you need to normalize things, okay? Because if you define the energy directly as the quantity above, the cost of transport lazily, then it's not a definite quantity in the sense that it's not zero when you take a measure with itself. So here I'm doing something called a polarization trick. I'm just renormalizing this energy of mu and u so that it becomes zero when it's applied on the same measure twice. Now, what I do in this regularized Wasserstein case is I do the same thing. I center it. It's a way of centering this function of two parameters, of two variables. Well, it turns out that these three quantities are interesting because they are linked, okay? You can see that the middle is basically moving, sliding freely between those two extremes, MMD and optimal transport. And there's a few things you can also say about their computational properties and their statistical properties. You remember I told you that when you use a tool in machine learning that computes quantities based on samples, it's both important to have something that is quick and something that somewhat converges to what you want, to the real density-based quantity. And so if you compare those two things, on the one hand, again, you have in the bottom something that's very clever, this optimal transport, but that doesn't work well with data. Because if you actually instantiate it with data, you get something that is a complex, a very costly algorithm, and a very poor statistical complexity. You remember I told you basically if you were to compute the optimal transport between two densities, or by only looking at some samples, then the quantities that you compute on the samples converge very slowly to the quantities that you get on the densities, underlying densities. On the other hand, a very nice feature of this MMD thing is there is no optimization, right? This is the very first thing we noticed is if you send the mass proportionally without thinking about it, it's as if everybody was talking to everyone, right? Every barrack is sharing freely with every front line and they just don't think about it. And so if you want, the less effort you make usually in statistics, the more stable you are with respect to the data. But it's somewhat it's a tautology, right? It's kind of stupid. If you're not working hard to do something, then of course mechanically you're robust to perturbations of the data. And then this is where you can see that first it's very cheap to compute it. It's just a question of looking at all of the distance between all of the soldiers, all of the barracks, and all of the frontline posts. That's the first thing. And because you're not working very hard, it's stable and it converges very well. And then you have a rate over 1 over square root of n. So if you want, you're either given the choice of doing something very, very clever, but that's very expensive and converges very, very poorly, or you're given the choice of doing something a bit stupid, but that converges very quickly and it's very, very, very easy to compute. So here what we do is that we show that somewhat you are in the middle with this regularization of optimal transport. So on the one hand, I showed you that essentially optimal transport is about doing those Sinkhorn iterations. Each Sinkhorn iteration is a kernel multiplication. So what's on the top, MMD, would just simply be summing this kernel matrix. What we do in Sinkhorn regularized transport is just simply multiplying several times by this matrix. And the other result that I didn't tell you about is this idea that actually this quantity has much better sample complexity than the Wasserstein distance. Because we are giving ourselves more room, we are allowing ourselves, to be a bit lazier, we recover in exchange something that has better sample complexity. And so we showed in the paper recently that the sample complexity of this quantity is basically 1 over square root of n, so it has the same sample properties than MMD, but there's no free lunch. Since I'm introducing some parameter that interpolates between the two, it has to blow up somewhat in dimension with respect to this parameter gamma. And this is what we observed now. Now, this is, if you want, the theoretical argument that says that this regularization makes sense. Now, I would like to go a gear up and say, okay, we've been computing Wasserstein distances, approximating them, worrying about how to, whether what we're doing is making any sense statistically, etc. Let's think more about the viewpoint of practitioners now. What practitioners want to do is compute this distance, but also have a quick way or quick insight on how to differentiate it. Okay, who's used TensorFlow or PyTorch or Chainer or whatever? Please raise your hand. Okay, I'm sorry, I should look at it here. Yeah, okay, so if you haven't, it's vital now. It's if you want to survive in this field, you really, really need to put your hands into this kind of automatic differentiation framework. And so what this type of frameworks give us is the very nice opportunity to just compute gradients on demand, right? Without thinking about them. And for tools in machine learning to actually have success now, it's nice if they can fit in nicely into those frameworks. In the sense that we can directly put whatever function that you want as in any pipeline, and then automatically differentiate through it using the means of those frameworks. So mathematically, the question is both, can we have nice differentiability for this Wasserstein distance? And I would say programmatically is, can we get a nice implementation of a program that is easy to backpropagate through? And so for Wasserstein, the answer is yes for both, and it's essentially using regularization. So let us just think about what I mean by differentiability for the Wasserstein distance. So if you're a programmer, you're given as input 2-point clouds with weights, A, B, locations X, Y. And there's two things you might want to play with in terms of differentiability. One of them is, what happens if I tweak a little bit the weights of one of the measures? So if my weight A, vector of weights A, is perturbed by some vector delta A, the delta A vector should sum to 0 usually to make things well posed. But I want to have an idea. Can I actually have an insight on, when computing the Wasserstein distance, or an approximation of it, of how this will vary? The other question that you can ask is, how does that work with a variation in the support? Okay? And so for both cases, what you want is some notion of gradient of the Wasserstein distance. However, if you think a bit about it, it's not so obvious that gradients make sense for probability distributions. They're different objects, right? It's not a vector space. Set of probability distribution is not a vector space in the sense that you can't just add up two probability distributions. You need to normalize for the total mass. And there is also the problem that you have the positivity constraint on the mass that is enforced. So all of those topics, how to play with the geometry of the Wasserstein distance in the space of probability measures, despite the fact that they're not a vector space, has been investigated a lot in pure mathematics. So what we're doing here is trying just simply to hack our way to some results that those mathematicians have already thought about a couple of years ago. So if you start using the original definitions of optimal transport, you can use convexity, and you can use, a little bit of writing and thinking about things to find what are the gradients of those quantities. They actually relate to the dual variables or the primal, the dual problem of the primal problem. But I'm going to spare you this thinking, and I'm just going to take the fastest route, which is simply thinking about this as a programmer, playing with those TensorFlow, PyTorch, Chainer, and all of those frameworks. So why? Why am I saying it's easy? Well, the Sinkhorn algorithm, for so far, I sold it to you as a simple way to approximate transport and a cheap way. But the fact that it was actually simple to program was very, very important. Because if the algorithm is simple to program, it means it's simple to instantiate in the computational graph of such frameworks, and it's easy to backpropagate through that algorithm. Why do I say so? Well, imagine that you are a programmer, someone tells you, can you compute optimal transport? And you say, oh yes, I have this idea of using the Sinkhorn algorithm. So here's how we do it. You give me a bunch of points x, y. I compute this matrix M, x, y. You give me the weights A and B. Maybe the weights are uniform, so that makes it even a bit easier. And then I just run this loop for a few iterations. And let's say I'm on a budget. I don't have that much time. So maybe I have 50 iterations. I'd run it until big L is equal to 50. And at the end, I just output you whatever I have. Okay? So that would be what is written there. Maybe I can write it this way as well. I have weights A and B's. I have inputs X's and Y's. I combine the inputs X and Y's to form a matrix of costs. So this is how you would program it. Then I use that matrix of cost and I exponentiate it minus the matrix divided by some gamma. That gives me a k. And then I just run the Sinkhorn algorithm for a while. And if you look at the Sinkhorn algorithm, it's essentially doing some form of convolution, like a matrix vector. You could call it a convolution. And then element-wise operations. So it's almost as if it was an activation, if you want. Ku, you take the inverse, okay, whatever Ku, and then you multiply element-wise by A. You do again this thing, you multiply element-wise by B, etc. So you run this for a couple of times. So it looks like a big stack, multi-layer neural network where actually the weights depend directly on the points X and Y's. And at the end, you output whatever you get, whatever cost you get. Well, I guess it's not a surprise for most of you here. You can actually compute the gradient of all that with respect to any of the inputs without any cost programmatically. And in terms of execution time, you just need to do backward pass, which has the same time as your forward pass if you have stored all of the intermediary computations. So there are slightly more clever ways probably to do this. Of course, there's ways to store more or less data, and some of the clever ways that you can think of is do it like implicit function theorem inversion and things like that. But this approach has proven quite resilient, quite stable, and has been used in a lot of work since about 2016 or 15. And let me say that there was an earlier application of this backpropagation through the Sinkhorn algorithm in 2011 that was done by Ryan Adams and Richard Zemmel in a different context. So this is an idea that's been around for a few years now. And this is definitely what I would encourage you to do if you ever want to differentiate through the Wasserstein distance. So let me see how much time I have. So this Sinkhorn approach is like one possible route. And differentiating through the Sinkhorn is easy. I hope I have convinced you of that. So let me now go switch gears for a minute and talk about something that's also quite popular recently, which is this idea of sliced approximation of Wasserstein distance. So again, you have to take a step back. Optimal transport is a very nice theory, but one, it overfits data, so it's very slow to converge to what you want in terms of densities. Two, it's very costly. What can we do to make it faster and maybe better behaved? One way to do this is to recall that transport in one dimension is trivial, okay? I explained this yesterday. If you want to remember this result, if I have two univariate densities, then it's very easy to compute optimal transport. It's just essentially computing the quantile functions of those densities and comparing those quantile functions directly. So this is one thing that was taken advantage of by a few people like Julien Rabin and Julie Delon and Gabriel Perret and I think another author a couple of years ago, when they said the following. They said, well, you know what, if computing transport in 1D is so trivial, why don't we take any point cloud in higher dimensions, project it randomly on a bunch of directions, and solve optimal transport in those lines, on those lines, and then we average whatever we get. Okay? So it's a cheap approximation. Well, it's not really an approximation. You're doing something different from optimal transport, but it looks a bit like optimal transport. Let's say it's just a related cousin of optimal transport. Well, this has had a lot of success. And the reason why it has success is it goes in both directions. It's very cheap to compute. So let me just help you parse this equation. I will call the sliced Wasserstein distance between two measures the expectation over some random vector in the sphere theta. Okay, so I'm taking any one direction in the sphere. I'm taking several of them. I'm computing the expectation on the right-hand side. And what is on the right-hand side is essentially the Wasserstein distance of the projection of the first measure and between the projection of the first measure and the second measure on the same line. Okay, so I'm taking those point clouds. I'm picking randomly one direction. I'm projecting everyone on that direction. And I'm computing the Wasserstein distance between those 2 point clouds and this real line. And then I'm taking another direction, and then another, and another, and I just do this cyclically. What people have done as well to cope with this high-dimensional problem with the Wasserstein distance is, I guess, what many people would think of doing. Imagine you have to compute the Wasserstein distance between two high-dimensional point clouds. Maybe they live in dimension 20,000. So this is typically what people in biology would have to face. Okay? Imagine that you are tracking populations of cells across time, and each cell can be described by a very long feature vector. And then you think, does it make sense to do optimal transport in such a high dimensional space? What you would do probably is do PCA first, project all of those big vectors onto a subspace, and they do optimal transport on that. And so this is what people have proposed as well. So let me just say that this might be a good idea. It seemed like a good idea, but it might be a problem. Let's think about this case, for instance. You have those two measures, the red and the blue, and suppose you do PCA first. So what is the first axis, the first principal component in this case? Can anyone draw it in the air? Okay, thank you. So it's a very flat line, right? PCA would just be, the PCA of those 2 point clouds, or two measures, would just be a flat line there. So imagine what happens when you project it. If you project, you get those two segments, right? This is what happens when you project in the first principal component. And in that case, the Wasserstein distance between the two is gone. So this trick of doing PCA first and then Wasserstein second might be a bit, might have surprising consequences. I mean, unintended consequences. So one of the things that we proposed recently is to look for the worst possible projection, in the sense that you want to maximize, as a function of the projection space that you're considering, the Wasserstein distance between your two measures once they have been projected on that subspace. So let me just illustrate this pictorially. We have two measures, blue and red, and what we'll be thinking about is what is the subspace which you can use to project the measures on that subspace and then get a Wasserstein distance between the two projections, which is maximal. So why do we want something maximal? Because it's very easy to get something minimal, right? If you project everyone on some orthogonal subspace, then everything collapses to 0, and so usually you never capture something interesting and meaningful if you look at the minimum. If you look at the maximum, it's basically you're trying to get the signal. You're trying to see where the action happens. Just like in PCA, what you will favor is axis of projections that seem to have the most variance, the most noise. Here's the same thing. You want to find the projection subspace which seems to discriminate the most effectively your two subpoints. So we have some algorithms to compute an approximation of this, but I will just skip this. So if you're interested, you can look at a paper that we published at ICML last year called Subspace Robust Projections, Subspace Robust Computation of Wasserstein Distances. So now let me switch to a few applications that I will very briefly mention, and then I would like to finish the talk on some recent research work that we have done with colleagues at Google. So there's lots of things that people have been using this Wasserstein distance for, and the most obvious thing that you can look for in the literature is the idea of Earth movers distances. So if maybe some of you, when they arrived in this lecture, they knew about Earth movers distance but not about optimal transport. And then they probably understood that actually it was the same thing. And it is the same thing. Except that Earth movers distance were proposed in the computer vision community a couple of 2 decades ago. And the idea at that time was to say we have two images. Computational power was scarce then. We had to deal with, of course, far less powerful computers. So one of the ways to compare two images was to look at their color palette, distribution of colors. So here you have the color palette of this image and the color palette of the right-hand image. And what people said is, okay, let's compute the optimal transport distance between those two color palettes, and then we get something that we can define as a distance between the images. So you did a bit of that yesterday. You computed somewhat this Earth movers distance yesterday between color palettes, except that you went a step beyond and you actually played with the interpolation between those two color palettes, which optimal transport gives you. Okay? Now, people have done that as well for text histograms, and this is also something that you did yesterday. And this was proposed about 4 years ago. People redefined again optimal transport and called it the word movers distance, but it's exactly just the same idea over and over again. It's comparing 2-point clouds and trying to find an optimal way to match them and using some geometry. And here the geometry is the one given by the word embeddings. So this slide sounds so 2015, of course. So here you can, this is the one that they use to illustrate their example. I'm thinking which one you could come up with now in 2019. There would be quite several creative ways to do something here. So I told you that so if you look at this, this is typical of how people would think about optimal transport for many years, which was essentially just a tool to compute how far things are. It's a retrieval tool. It's just a fast, not a fast, usually a costly way to compare two histograms. I hope I have convinced you that now we have access to faster algorithms. We can do a bit more than that. We can think about differentiating this optimal transport cost and using optimal transport within a learning pipeline. So let me just show you, I have a slide. So this slide is actually by Justin. So we gave a NeurIPS tutorial in 2017. He liked this. So actually you probably recognize because you had this Grammy tricks yesterday. You had the slide on using gram matrices and Grammy tricks. So this is Wassersteinization. So this is copyright Justin. So introduction of optimal transport into an optimization or learning problem. So instead of, if you've heard about the kernel trick or maybe sparsity, basically you are going to drop some Wasserstein flavor into any learning pipeline where you think it's relevant. And typical pipelines where it's relevant is when you're learning with point clouds, you're learning with histograms, you're learning with probability distributions. So if you think about what kind of problems involve the Wasserstein distance, there's at least one which I know you have all used at some point, and that is k-means. So this is a fascinating thing. I mean, I think it's an interesting fact that k-means is actually a Wasserstein problem. So let me just phrase a Wasserstein problem first, in an abstract sense, and then make the link with k-means. Imagine you have a probability distribution which has a lot of atoms. It could be continuous, but it has a lot of atoms. And you want to approximate it with another measure which has far fewer atoms. Okay, it's going to be a measure supported on a few points. Imagine I give you a data measure with just 1 million, sum of 1 million Diracs, small Diracs, and I'm telling you I would like to approximate this with a measure which has like 10 Diracs. And the approximation I'm going to measure in Wasserstein sense. I'm going to say, I want to find the approximation that has a small number of atoms, which is the closest in Wasserstein sense to the original data measure, where this turns out to be exactly equivalent to the k-means problem. So minimizing this, Wasserstein 2 of a measure mu which has k atoms to a measure of data is the same thing as k-means. And so k-means somewhat is a particular case of the Wasserstein minimization problem. Then the other problem that you can think of, and that we saw yesterday, was this idea of interpolating between two probability distributions. I have this measure on the left, a measure on the right. I want to create the interpolation between the two. And then, arguably one of the greatest achievements of optimal transport theory is this JKO scheme that people have studied for now about 20 years, which shows that you can rewrite a lot of PDEs as gradient flows in the space of probability distributions endowed with the Wasserstein distance. So for those of you who are familiar with proximal methods in optimization, you know, when you use the Proct operator, you're essentially smoothing a function with a small Euclidean norm, and then going through optimization by iteratively doing optimizations of, you know, optimizing a function plus a small smoothness, where you can do exactly the same idea in the space of probability distributions using the Wasserstein distance, and you recover a lot of very important PDs. But I will just not talk too much about this. So the first example of a Wasserstein learning problem that I will consider is this idea of learning averages of measures. So remember what I mean by average or interpolation is just something that's in between, something that's in the middle, and the way you define the geometry directly encodes what you mean by in the middle. If the geometry that you use between densities is the L2 distance, then the measure in between the blue and the red here, the purple one, it becomes the sum of the two. If I'm using the Wasserstein geometry, then the measure in between the red and the blue here is this purple mass in the middle. So more generally, maybe I don't need to restrict myself to just two measures. Maybe I can consider more of them. Let's think about 3. And what would it mean to compute a Wasserstein Barycenter? Well, a Barycenter is essentially something that's not too far from other points. And the way you quantify the fact that it's not too far is that you sum the distances of one point to all of the other points and try to minimize it. And you can play with weights if you want to compute a Barycenter with different weights. So this is the type of problem that we will be addressing, and this is the very first type of Wasserstein learning problem that we can think of, computing the mean. I mean, if you have a bunch of things, usually you like to compute the mean, like a template. When you have vectors, it's trivial. You just sum those vectors and divide by n, the number of points that you have. Here in this case, in the Wasserstein space, you need to solve an optimization problem. And so let me just show you what it would mean, at least intuitively, in the very simple case where you have univariate measures. So now, instead of having 2 sensors in the room that measure temperature, let me throw in a third one, okay? So the top density is the temperature histogram of that sensor. The red one is that sensor, and the green one is that sensor. And at the end of the day, you have to come up with an average of those three sensors. And here what I'm showing, and this is an animation that was done by Justin, you will see this little ball moving around, and what the little ball stands for is what is the weight that I'm giving to each of those three sensors. So when the ball is on the top, it basically means that I'm going to overweight the blue measure and give a very small weight to the red and the green. And here, by just having the ball moving around, I'm just interpolating in different ways those three densities. And on the right, what you can see is basically what you would propose to someone asking you for a summary of those three densities. On the right-hand side, the L2 mean is just the average of those densities with different weights. So you can see this elevator game, you know, the peaks of those three measures going up and down. And on the left, you have the Wasserstein average. So here, I think you can feel that it's doing something fundamentally different, which is playing, you know, with this transport the values. So taking a step back here, there's something actually quite trivial going on. It's not as complicated as what it looks like. What we are actually doing here is on the left, when we compute this Wasserstein mean, we're actually averaging quantile functions. Okay, remember that optimal transport in 1D is just about quantile functions. So rather than averaging densities on the right hand, on the bottom right, what I'm doing in the middle is I'm computing the quantile functions of each of those three densities, averaging them, and then taking the inverse and derivating again to recover the density that corresponds to this average quantile. So the first time we started doing this for maybe more ambitious probability distributions was in a paper in 2014, where you can probably imagine what I did. I simply replaced the definition of the optimal transport distance, the Wasserstein distance, by the regularized Wasserstein distance. And so what I tried this idea on was this collection of three ellipses, you know, that are on the plane. And again, I represent each of those images as a probability distribution where the ink is distributed. Okay? And so if you compute the Wasserstein average of those images, well, so this is the regular L2 average, and this is the Wasserstein average. So to me, this was a sign that something interesting was going on there. The fact that you compute an average of those ellipsoids which are scattered all around the map, which usually have no regularity. You know, you can see that they kind of cross each other. There is not a single image there that really looks like an average of ellipsoids. Well, if you compute the optimal transport average, this is what you get. So it's at least it seems to provide something that agrees with your intuition of what a good average of those shapes would be. And again, this is without encoding any regularity. So any regularity in the image that you want as an average. You're just saying, let's compute something that is closest as possible in the Wasserstein sense. So I will skip this because this is a bit technical. So there's many applications where you can think this could come handy. So in the planes with the ellipses, of course, the metric was very simple. It was just the distance between pixels. But there's lots of scenarios where you can think of, I have a lot of signal that is scattered in the geometric space, and I would like to average it. So one example was in brain imaging. So here is the context. In brain imaging, we're given patients, we're showing to some patients some visual stimulus. And we are able to infer from some measurements which area of the cortex have been lit up. Where is basically your brain flowing some blood, you know, when you see something. And based on that, we can see for several patients basically how we can remap all of those, their actual locations, to some model of the brain, a canonical model of the cortex, and then compare them. And then by looking at where that thing seems to be happening, we can say, there seems to be some area in the cortex which is responsible for this. So I think the visual stimulus here is whether you're looking at someone who's famous or not. And this seems to light up a different area of the brain. And so here is the activations are for people, for famous people. And because of variability between us, of course, in our brains and all of the process, it's not going to be exactly the same area that is lit up across all of the subjects, right? Maybe someone will be slightly there, and then, I mean, there is going to be some spatial variation. For each of the people that have been involved in this study, however, what we get is a probability distribution that seems to say there is some intensity in those areas. Now, what would be the naive way to average it? Well, it's basically just like the L2 average that I showed earlier. You just pile up all of the measurements, divide by a number of people that have contributed to the study, and you get this kind of scattered, light zones that are on the cortex. And this, you say, this is the average activation. But that doesn't look like an average activation in the sense that it's something that's very fractioned in several areas, and it's a bit the same idea with the temperature histograms, right? If you really want an average that looks like, so if you have, again, the temperature sensors, if you have one sensor that's blue and the red, if you want an average sensor, the purple on the top the purple density on the top does not look like an average sensor. It's more like the Wasserstein Barycenter that looks like a sensor. Yes?
One question, you compare it to A2 average, but what would be if you think about other measures, for example, mutual information?
Yeah, so if you were to use Kullback-Leibler averages, so typically here this would completely blow up, because this would blow up. There would be a problem there with the Kullback-Leibler. So there's, again, I don't want to go to, there are several ways you can set up this for Kullback-Leibler. There is left Barycenters, right Barycenters of Kullback-Leibler, mutual information, but it all boils down to Kullback-Leibler. I mean, if you were to use, I mean, so in all of those cases, because the supports do not overlap, computations blow up. And what I would really, I would really bring this message is there is no geometry in Kullback-Leibler. You never take into account the fact that an intensity here is not too far from an intensity there, where it's very far from this one. Kullback-Leibler is completely oblivious to geometry. So it's not only the fact that computation is likely to blow up, although you might find ways to make it somewhat work by smoothing out things and things like that. But when you do the smoothing, is essentially what we're trying to do is put some geometry in there. Smoothing is just geometry. Smoothing is just putting a Gaussian, a Gaussian around the point, and the Gaussian is using the geometry. So here it would be in the cortex. In the example of the cortex, it would be basically using some kernel, blurring kernel to make things. And of course, if you start blurring the kernel big enough, and actually this is already blurred, but if you start making big enough, then you get eventually an average that seems to be like a big blurb. But smoothing it right is a big problem. It's not easy. So for all of these applications, I think KL is a fairly poor choice. I mean, for geometric applications. It's a very clever, so this goes back, this is a bit hand in hand with my previous discussion on what happens in high dimensions. In high dimensions, geometry is no longer that reliable. And so it makes sense to use Kullback-Leibler or MMD, which are oblivious about geometry somewhat. But in low dimensions, I have other slides. If you want, I can share them with you after that. When you illustrate it in 1D, Kullback-Leibler just does nonsense. I mean, it's as soon as the supports are slightly far apart, it's just blurting out nonsense.
I'm just wondering about the results more.
Yeah, of course. So here we didn't even think of computing them because it just blows up. Actually, there's if you even think about the geometry that is if you think about the Gaussians, space of Gaussians in 1D. What the Kullback-Leibler divergence, the geometry that is applied by Kullback-Leibler divergence is hyperbolic. So basically you get to Kullback divergences that go to infinity if the variances become very small. So the divergence between two Gaussians, even if they're very, very short, I mean, even if they're very close apart, if their variances go to 0, then the divergence blows up to infinity. In the Wasserstein sense, if you have two Gaussians that are very close to each other in terms of means, and their variances go to 0, then it's stable. It's just the distance between the means. Question? So this is like, so maybe one of the things that I can say is that for this kind of averaging of distributions in geometric spaces, the Wasserstein distance makes a lot of sense and has been used, and there's lots of extensions of this that have been proposed in neuroscience recently, where the Wasserstein distance is not only used to compute Barycenter, but it's also used to enforce some kind of regularity between signals and regression coefficients and things like that. So there's some interesting work. So one of the things that Justin proposed around that time, which is somewhat a nice generalization of this Barycenter concept, is imagine you have a web of histograms. You have a web of probability distributions that are scattered all around, and for some of them you know the histograms, and for some of them you don't. So you can think of, for instance, one example is you have a network connecting sensors, and each of them provides a temperature histogram or a wind direction histogram. For some sensors break down at some point, and so you want to recover the value or the distributions of those sensors. And you could do this by basically computing this generalization of the Wasserstein Barycenter energy. It's something that says, okay, I don't know what are the values of the histograms at those question marks, but let's just minimize the distance of those question marks to their neighbors that I know. And then you can recover some. So this Justin called Wasserstein propagation. Now let me just present, show you how you can even play with the Sinkhorn algorithm and all those things by doing something called an inverse Wasserstein problem. So I hope I have convinced you in the last 2 or 3 slides that there is one thing you can do computationally that works, which is compute Wasserstein Barycenters of signals. So if you give me a few points, bi's, and weights lambda i's, I can find a Barycenter of those bi's with weights lambda i's that seems to play the part. You know, it was all of those. You remember the cow, the ring, and the duck. We were playing with those Barycenters. We were playing basically with combinations of those points in the Wasserstein space. We have algorithms to do this. What we would like to do is, given a new example, can you find the weights that seem to reconstruct this example? So let me just show you this picture, which I think is a bit more revealing. So here I have 3 shapes, 3 probability distributions, and they are set up in this triangle. So on the left and on the right, it's the same shapes. So I call them P1, P2, P3. So imagine I have a new shape that pops up. The idea of regression, or regression with simplex constraints, if you want to restrict your weights to be in the simplex, is to reconstruct the input, this measure, with a combination of what you know. Okay? This is the fundamental idea in regression, is if you have a variable and you have other variables that you can pair it with, you can try to reconstruct this target variable using a linear combination of the other variables. So in this case, it would be find on the left-hand side. I'm actually thinking about the left-hand side of the slide. If you have this new shape that pops up, can I find a linear combination of those 3 atoms that seem to match? And you can measure the loss or the difference between your reconstruction and the input shape the way you want. I mean, it could be Wasserstein, it could be L2, anything. So this is what we show on the left. Actually, if you look for the shape, which is a linear combination of the 3 shapes, that is the closest in L2 sense, you get this blue thing. And if you want to get it as the closest as possible in the red sense, in the Wasserstein sense, you get this red thing. So they seem to more or less give the same result. The kind of problem that I'm going to address here is different, and it's a lot more challenging. It's more fun if you play with geometric data, and it's the following. I am going to consider the same 3 atoms, except that as combinations, I'm not going to look at linear combinations, that is sums. I'm going to look at Wasserstein combinations, Wasserstein Barycenters. So immediately, if you just look at the 2 triangles, the blue triangle and the red triangle, you see, or sorry, the blue and the pink, you see an obvious difference on what I mean by interpolation between the 2. On the left, it's just L2 average, and on the right, it's just Wasserstein average. So I think there was a question yesterday about what would be the L2 average of those 3D shapes. Well, this is roughly what you would get. This is a 2D example on the left. You basically see like the fading original shapes appearing more or less strongly depending on the weights. On the right-hand side, what we have is the Wasserstein average. And so what I'm asking now is, can you recover, given an input shape, something that mixes those shapes on the right in the Wasserstein way, in the optimal transport way, and that looks like it. And so I'm going to skip through the details, but what this means to do these computations, what we need to do is basically differentiate the Sinkhorn algorithm, automatically backpropagating through the Sinkhorn algorithm, and I'm going to spare you the details because it's relatively complicated, but here is one very simple example where we use this in graphics. You have a collection of 5 3D histograms, volumetric histograms. Those are bears. There is one histogram that is given to me. It's an input. It's a bear that's been tortured. You've just cut the arms and dug a hole in it, etc. And then what you would like to do is find a barycenter, an optimal transport barycenter, Wasserstein barycenter of the 5 shapes that is as close as possible to this input shape. And this is what we get, actually. The projection that we would get is this thing. So it helps you somewhat do reconstruction in the Wasserstein space. So another example is in this color histogram world, where instead of just doing color grading, color projection between 2 images, as you did yesterday, we have one image who defines this 3D histogram, this 3D density, and we try to, given a collection of other images, find a linear combination, a Wasserstein combination of those 4 histograms to compute the best representative of that input color histogram and do color regrading. So it's not I don't think it's a revolutionary application, but it's one that illustrates this approach. And the other thing that we use this for is for brain imaging. Imagine you have a brain MRI scan. You can see your brain, and you would like to project it on the space of Wasserstein barycenters, optimal transport barycenters of brains. So it's quite ambitious, but it seems to work much better than Euclidean projection. Let me just skip this, otherwise I will be short of time on the rest. So we also did some Wasserstein dictionary learning. There's also a lot of work going on in domain adaptation using optimal transport. So use optimal transport basically to relabel another test set for which you don't have labels for. And the mechanism to do this is using optimal transport as a prior. You think that it would make sense if you have a labeled data set to transport it to a unlabeled data set and use basically the labels of the points you transport from to the points where you transport to. So this is a fairly direct application of transport. There's also been something called learning with the Wasserstein loss, which is minimizing the Wasserstein distance between a histogram and a histogram that you learn. So those are all generalizations where you basically think about trying to use this Wasserstein distance as a way to measure the difference between probability distributions or point clouds or histograms of words, etc., as opposed to just Kullback-Leiber or L2. And so this is really this idea of Wassersteinization that Justin put forward. In life sciences, what you did yesterday for color histograms is more or less what people have used in life sciences to compare point clouds of cells in dimension 20,000. They were computing the optimal transport and they were saying, okay, if this cell at time 0 is transported to this cell at time 1, it means probably that this is the way the cell has evolved through time and has differentiated itself, etc. So there's a, if you like, this idea of optimal transfer, we want to be convinced of a strong case study for using them. This is a very nice paper. And so this brings me to the very last talk, the part of the talk that I will need to deliver in a very short time. But I will be a bit fast, and I'm sure you will follow most of this because it's been a few hours we've spoken about optimal transport. Here is one interesting generalization of optimal transport that I would like to share with you. And it boils down to something very fundamental, which is sorting. So if you think about sorting, it's probably one of the very first algorithms that you were taught when you were in university or when you started programming. So what is the goal of sorting? The goal of sorting is given a list of numbers on the real line, real numbers, to put them in an order such that they are increasing. So of course, one of the challenges, I think conceptual challenges of sorting is that it seems pretty obvious to do this when you actually put the numbers on the real line, like I did there. So if I put, here imagine I have x1 to x5, and when I put them on the real line, it turns out that x3 is on the left, x4 is second, x2 is third, etc. But of course, we need algorithms to do this automatically without having to draw things on the real line and looking at them, right? So here, what I call sorting is getting the sorting permutation. Something that here would be 3, 4, 2, 1, 5, because it tells me that the third element of the list is the smallest, the fourth element of the list is the second smallest, etc. So I think we all share, we all understand this. Now, there's two things that you use sorting for usually in your algorithms, as in machine learning. One is the vector of ranks, and one is the sorted vector. So what do I call the vector of ranks? It's essentially the inverse permutation, the inverse sorting permutation. What does it tell me? It tells me, well, you give me 5 numbers, and x1 turns out to be the fourth, x2 is the third, x3 is the first, x4 is the second, and x5 is the fifth. Okay? This is the rank, what I call the ranks. And the sorted values is just simply what you read on the line. It's x3, x4, x2, x1, x5. Okay? And so we need sorting and ranking for many things in machine learning. And maybe the most obvious is k-nearest neighbors. When you do query k-nearest neighbor, we find the list of closest points, and that involves ranking, maybe ranking partially the list, but at least it involves this idea of ranking. The other place where we use ranking and sorting a lot is when we evaluate the performance of a classifier. So typically, we all train using a mixture of cross entropy or some form of regularization of that. However, when we deliver an algorithm, a classification algorithm to a user, what we usually say is this has accuracy 93%. Or we say top 5 accuracy of this image classifier is, let's say, 96%. And this is what people agree on. Cross entropy is a trick that we use for training, but it's not something that we use as a test metric. So we use a lot of those rankings and sortings at test time, very often, and not so much to learn. And one of the reasons why we use them at test time is because from a mathematical perspective, they're pretty badly behaved. Although they're very intuitive as CS 101 algorithms, mathematically, there's one problem, big problem with ranking and sorting, which is that they have no differential information, interesting differential information. So if you think about the ranking vector, here I have perturbed, for instance, the value of x4. I've added a small value to x4. The ranking vector hasn't changed, right? I just moved a bit, slided a bit this value. The ranking has stayed exactly the same. And what might happen is sometimes it might flip, but this is discontinuous. And if you look at the sorted values, vector of sorted values, the output basically only depends on one of the inputs, and that's essentially which one was in that place. So if you were to look at those two functions from an abstract point of view, The ranking function is just simply a discrete valued map. It maps an input to a vector of integers. And the sorting vector, so it's a map that maps a vector to a vector as well. But here it's a map which is piecewise linear, and it doesn't vary in a very interesting way. If you were to look at the Jacobian, basically you would recover the permutation matrix. So because ranking and sorting has so badly behaved, when people try to use them in a learning pipeline, they need to come up with a lot of tricks to somewhat get around the fact that those are not differentiable. And in many fields in stats and machine learning, you see somewhat attempts at making this differentiable using a surrogate. So what we will do, and I try to do, is rather a more direct approach where we directly propose an operator or a rank operator and a sort operator which are programmatically differentiable everywhere. And there are approximations of sorting and ranking and sorting, and they are arbitrarily close to the true ranking and sorting vector outputs. So this is more or less the goal. The goal is to have those curves that when epsilon goes to infinity and a lot of regularization, it's basically something that is quite flat. And when epsilon goes to 0, we recover something that is the staircase or those, spiked angled curves. And I want to be able to set this, parameter epsilon the way I want. And the way we're going to do this, so the motivation for this is, I would say, is very, very simple. We just want you or other people in TensorFlow or differentiable frameworks to be able to insert sort and ranking inside their pipelines, their learning pipelines. So typically ranking and sorting appear a lot at the end right now to define those top K accuracy, etc. But we could think about any learning pipeline that at some points makes some sorting to decide to make a decision. Then we will make it soft, basically. And in the near future, what we would like to use this for is to be able to impose directly constraints or regularizations that depends on quantiles of the functions or rankings of the functions for certain individual or certain characteristics. So with this approach, you could, for instance, impose that you want that if you do regression, that the median of your output is equal to some value or is not too far from some target value. And at this point, it's quite difficult to do so. So here is the way, some related work, there were proposals to do this in about 10 years ago and another one at iClear last year. And they rely on some nice ideas. I'm sorry, I don't have the time to explain them to you. Otherwise, I won't have the time to explain my idea. So if you're interested, please look at the slides, and I'm happy to answer questions. So the way we will do this is using transport. So now that you come out of a 4 hours lecture on transport, you know what this is. So it's this idea of finding a way to transport optimally mass from some point cloud to another one. And I'm saying I'm going to generalize sorting using transport, but that doesn't sound necessarily like a good idea. So let me just explain a bit my reasoning. So we know that when we do transport on the real line, that essentially what we're doing is sorting, because we need to compute the CDFs, we need to compute the quantile functions, etc. So if you want, the logic is as follows. Optimal transport is this very tricky problem that is n plus m is cubic. Thank God, when everything is on the real line, it's much, much simpler. We just need to sort. So the direction goes from sorting to transport. Okay? Sorting simplifies transport in this very particular case. So what I will do is something that sounds very stupid at first sight, which is, well, actually, you know what? I really like transport. And even if sorting is very cheap, I'm going to solve a sorting problem using transport. I'm completely fanatic about transport, and I'm not going to sort. I'm not going to use clever sorting algorithms. I'm going to somewhat recover your sorting information by solving an optimal transport problem, no matter what the cost is. And then I'm going to show you that because I'm more clever than sorting, I can somewhat generalize it. I can do some things that sorting cannot do. which are useless, but still, I mean, I can show that I have more, you know, theory and everything. However, what you can imagine that I will do after that is introduce the regularization of transport, Sinkhorn algorithm. And you saw that this was a fast algorithm that is basically quadratic in time. It's n times m. And this is a few Sinkhorn iteration. And the most important thing is that it is differentiable. And so this allows me to recover something that looks like a differentiable sort using optimal transport. So let me look at the time. So maybe I have the time to flip through a few slides. So you know about transport. By now I think you have this clear idea that it can be solved by instantiating a linear program. This linear program, you can visualize it as, you know, there is a cost vector, which is a matrix of pairwise distances. There is a set of matrices, transport plans that you can consider. You can compute P star, which is the optimum, and you can do this in cubic time. Now, this is the hard, you know, the way where you want to prove that you're actually good at linear programming and you understand linear programming theory. What I told you though is that when the data is in 1D, there is this very simple trick, which is to simply compute the differences between quantile functions. So how would you compute this here in the real, for data here? Well, okay, I'm sorry, this works only when the cost is convex, as you remember, right? So here what you would do is just simply put your two measures and then build this staircase, right? You compute the CDF, the cumulant density function, or empirical distribution function, which is just simply the staircase where the steps height depends on the weight and their location depends on the point x. And then I told you to compute such a staircase you need to sort the points. So sorting information is needed at some point. Okay, this is the empirical distribution. And then I told you actually the only thing you want to do when you do transport is compare the quantiles. So quantile is like the inverse of those, generalized inverse of those stairs, and just comparing them one after the other, integrating the difference like this. Okay? So I just want to emphasize again, theory led us to the right-hand side. Okay? Theory told us that actually if you are comparing 2-point clouds on the real line, you just need to compute the quantile functions and integrate that. Okay? That's the trick, if you want. I could actually solve optimal transport the generic way, the one where I actually run my network simplex solver, and that's what I wrote on the left-hand side. Now, let's look at what happens. Yes? You mean when sorting or when? Okay. So they have a very good point. Here, on the one hand, when I'm talking about sorting, the only thing I'm considering is red. And here I'm saying I'm going to use red and blue. And still, you're right. I didn't explain yet. I've sorted red. I've sorted blue. I've computed. Here I'm sorting both, right? I'm sorting red, sorting blue to get the empirical distribution, and then I'm comparing the quantiles. So your question is, where can I recover sorting from that? Sorting the red from that? Well, okay. If I give you red and blue, and out of that I give you the sort for red, it's as if you had blue. I mean, blue was a distraction, but it helped me get the red. That's exactly, but you have a very good point. When you sort, you only look at red, and here I'm going to present a mechanism to sort red that introduces some blue artificially just to get the sorting of the red. And this is why it seems overkill. It seems very complicated, but I will explain how you get it. So again, this result is fundamental in math, but what we are using it for is just for sorting for now. So let me just walk you through an example. Let's drop weights, because weights is complicated. Let's drop the fact that there's different number of points. Okay, I have a set of blue values and red values, and they have all the same weight and it's same number. So how basically does the logic of computing the CDF and quantile, etc., it basically says, I'm going to sort the values of the reds, I'm going to sort the values of the blues, and the only thing that I'm going to do is say, I'm matching the first red and the first blue, the second red and the second blue, the third red and the third blue, etc. And this is the optimal transport that you actually compute. So again, if you want to run it the difficult way where you solve the optimal transport, etc., you can do it. But there is a very fast trick to compute exactly the same value using this pairing argument. First and first, second and second, third and third, etc. And by this same argument, you can also recover the optimal transport matrix. What the optimal transport matrix is it's a matrix, a sparse matrix of ones, which basically has a value 1 with the first red and the first blue, the second red and the second blue, etc., etc. Now, here, to go back to your question here about why do I have the blue, here I have an equation that basically says, if I were to run the optimal transport solver on the left, P star, I would recover something that is basically pairing sorted values, reds and blues. So why about the blue? What is it? Do I really need the blue? And here is the argument that you may be waiting for, is if I'm free to choose the blue whatever the way I want, because I haven't said anything about the blues, let me just choose them sorted. And I will even go beyond that. I will choose them such that the values are just very simple. Let's say it's 1, 2, 3, 4, 5, 6. If I have n points on the left, it's going to be 1, 2, 3, 4, 5, 6. So here, I still need to sort the red. The blue is already sorted. So what I get is the first red goes to 1, the second red goes to 2, the third red goes to 3, etc. And the optimal transport matrix on the left is actually equivalent to the sorting permutation given in matrix form. So let me just try to give you an idea of what this generalized sorting does. So there's two ways. I'm going to propose two ways to sort things. So we start with red. Red is just a bunch of values, 6 of them. You would go sort function, you compute the sorting permutation, and that gives you the rank and sort vector that you want. Okay? So this is like everybody does that. Okay? You just call a sorting function. So there's a bit of a story there. Imagine there is a line and people are racing on it, and then at some point you want to make a ranking of who is the last and who is the first. You ask everyone for their positions, and then you start comparing all of them. You say, okay, so the x1 is ahead of x2, but it's before x5, etc., etc. So you make all those pairwise comparisons. You're comparing all of the reds together, and then you get the ranking permutation. Sorting permutation and the ranks and the sorted vector values. So this is the standard route, I think we all agree. Here, the second way to look at things is a philosophically fundamental way. You say, no, I'm not going to sort them. I'm not going to compare my players between them. The only thing I will do is I'm going to do the following. I'm going to put a few milestones in the race. The milestones are, written in marble. It's like they're set forever. It's 1, 2, 3, 4, 5, 6. And I'm going to solve the optimal transport between those red guys and the blue milestones. And what is important conceptually is that I'm never going to compute the distance between the reds. I'm never going to say, is x2 from x1? Remember, when you solve the optimal transport problem, you never need to do that. You only compare input and output measures. And what is nice is that after computing the optimal transport problem, I know that the first red point is going to be optimally mapped to the first milestone, etc., etc. So looking at who reaches which milestone, looking at who is assigned to which milestone, I can recover the permutation, sorting permutation information. So using that, I can recover all of my ranking information and sorting information using this P star. However, I think by now you understood that I like optimal transport, but if I wanted to defend it to you, it would be a bit fanatical, right? Here, sorting is just n log n, and here I'm proposing you a sorting algorithm that is n cubed log n. So that's not very clever. However, there's a few things you can do with this different approach which you were not able to do with the first one, which is you can generalize it in subtle ways. So one of the ways you could do this is maybe increase the number of milestones. And so because of optimal transport here, people will start splitting their mass, across milestones. You could decrease the number of milestones. And because of that, essentially 2 people would be mapped to 1 milestone. You can start playing with weights. So maybe one of the milestones is heavier than the other, and so you're focusing on one milestone in particular. So maybe if what you're interested is who is in the middle of the race, then maybe you put a big milestone on the left that captures most of the last guys, big milestone on the right that captures most of the guys in the front, and a very small milestone in the middle that captures the people in the middle, and etc., etc. And so there's lots of formulas that you can come up with each time generalized sorting. Now the way we do things is not that way, of course. If you were to solve sorting using optimal transport, that would be far too costly and still not differentiable. So what we do is we do this step of using regularized Sinkhorn, and this is what we essentially do. We redefine sorting, ranking, and sorting operators using the outputs of this Sinkhorn algorithm that we've iterated a few times. And with this, we get differentiable ranking and sorting operators, and this allows us to do a lot of interesting things, such as proposing differentiable 0-1 losses, differentiable top K accuracies, and etc., etc. So thank you very much for your attention. I'm a few minutes late. Thank you very much.